All right, well, this slide just kind of reviews what we talked about on the previous video. We see that the rate of the reaction changes and that the rate itself actually is the change of the concentration of the product with respect to time. And it's the negative change of the concentration of reactant with respect to time. And this slide also reviews some of the things we've talked about so far and also tells us a little bit more about the rate constant, okay? So in the last slide, the last video rather, we saw an example where the rate was equal to the rate constant times the concentration of NO2 squared times the concentration of O2 to the 1th power. And each of these numbers were the reaction orders for those given reactants. We can calculate a so-called overall reaction order, and we get that by adding these up. So we'll add up 1 and 2, and the overall reaction order is 3. And the reason why we care about the overall reaction order, because that's going to tell us what the units need to be for our rate constant here. And so that's what this table is saying up here. We can have a 0th order rate constant, and this is what those units will be. If we have a 1st order overall rate constant, that's what its units will be. And then you see we've got 2nd order, another kind of 2nd order, and then even a 3rd order. And for each of these, the units change because the rate is always going to have to be in molarity per second. And so the rate constant is going to need to change as we change how many of these concentrations we're multiplying times it. So by now we've seen a couple of different examples of rate law expressions, but how do we determine the rate orders and the rate constant for a given reaction experimentally? And that's what this slide covers. And so I'm going to start with the method of initial rates right down here. So I'd like you to imagine the following chemical reaction. Little a moles of substance big A plus little b moles of substance big B reacts to form little c plus little d big D, like so. Okay, so now let's assume the following rate law. Let's say that the rate equals some rate constant. We don't know its numerical value, we don't know its units, and since this arrow is one directional up here in the reaction, that means that the rate law is only going to depend on the reactants. We'll see examples of how the rate law will eventually depend on the products as well, but we get to that at a later time. And then this is going to be raised to some power, and let's just call that I for now. And then B is going to be raised to some other power, and either one of those or both might be 0. They might be 1, they might be 2, who knows? And so now the question is, how do we get those numbers, K, I, and J, experimentally? Okay, the way that we do it is we run experiments where the concentration of B stays constant, at least at first. And the concentration of A is changed. So that means there's going to be one concentration of A, and it's going to produce a certain rate of reaction. And then there's going to be a different concentration of A that's going to produce a different rate. Okay, so we'll now have two different rate law expressions. K, and this is that first concentration raised to the unknown I power, and the concentration of B raised to the J power. And then we've got a second rate, again K, but this time the concentration of A is that other value, and then B is still remaining constant. We're going to have to divide these two expressions. So rate 1 divided by rate 2 is going to equal K, A, 1I B to the J, K, concentration of A, 2 to the I, concentration of B to the J. Since K is always the same, that's going to cancel out. And since B was also held the same between these two experiments, those will cancel out. And so all that we're left with is just the rates and the concentrations of A. Now the next step is to take the natural log of both sides. So we're going to get the natural log of rate 1 over rate 2 equals the natural log concentration of A in the first case, concentration of A in the second case. But we can just pull that I out to another parenthesis on the outside. So let me delete those little i's. Oops, I erased a little too much there. Then we get this I out here like this. But then we know from the rules of logland that we can just pull that I out to the front. So we get I log concentration of A in the first experiment, concentration of A in the second experiment, and there we go. So at this point, we've measured the two rates experimentally, and we've measured the two concentrations experimentally, and we can algebraically rearrange, and we get the log of rate 1 divided by the rate 2, and then inside this one, concentration of A in the first experiment, concentration of A in the second experiment, and that's how we find I. We find J in the exact same way, but this time the concentration of A stays constant and the concentration of B varies between the two experiments. And then once you know all the orders, then K can be found algebraically using either of the experimental results. And I'd like to do an actual example of this right now. So I'm going to put down a table of measured rates and concentrations, and we'll solve the problem together. All right, so here's the sort of data that you would obtain after running an experiment for determining the rate law, kinetics experiment. And we're going to use the same rate law expression as we did above, which recall is just the rate equals rate constant, concentration of A to the I power, concentration of B to the J power. And we're going to use that formula up there in order to calculate I first. And we're going to need to use these two data points here, because as you can see, the concentration of B stays constant. It's the concentration of A that's changing. So I equals the natural log of the two rates divided by each other, 3.4 times 10 to the negative fifth, and 6.7 times 10 to the negative fifth, divided by natural log of the two concentrations, 0.25, 0.050, like so. Now when you plug this into your calculator, I equals 0.98, on and on and on. And most of the time, these rate orders are going to be integers. And that's close enough to an integer that I can safely say that's going to be a rate order of 1. It's pretty rare that you see a reaction that doesn't have an integer rate order, though it does occasionally happen. Okay, let's use a different color to represent the rate order, the method of initial rates for those two reactions right there. Now we're finding J, because as you can see, it's the concentration of B that's changing. This is going to be the natural log of the two rates divided. There's the first one, 1.39, 10 to the negative 4. And then we're dividing by the changing concentrations of B. Okay? And when we plug that into our calculator, we get something like that. 2.03. And again, that's so close to an integer that we can just say that's going to be a second order part of the reaction. Now the last step is to find K. So we're going to plug in a rate that we know as well as concentrations and the orders that we found, and then we're going to algebraically solve for K. So let's choose everything from this row right here. 3.4 times 10 to the negative fifth for the rate equals that unknown rate constant, 0.025 for the concentration of A, and 0.018 squared for the concentration of B. And again, we're using this J that we found there, and we're using the I that we found right there. And when we solve for K algebraically, we get a rate constant of 4.20 moles per liter to the negative 2 power and seconds to the negative 1 power. And we choose those units because this is an overall rate reaction order of 3. So it's a third order rate constant. And those are the units that we need to cancel out the concentrations in the final expression of the rate law.